We're going to go over the mathematics of time equivalence of money. And we need to adopt a symbolic notation so we can understand it. In this symbolic notation, P stands for the present value. The value of the money at time equals 0. F stands for some future value. I will stand for either the discount rate or the interest rate. And then we're going to put N, what's called the number of compounding periods, up in the equation as well. We got to do some units. P is measured in dollars, F in dollars, but the interest or discount rate in dollars per dollar, so that would be percent per unit time. And the number of compounding periods, which we haven't talked about yet, is how many times the interest would be added to the principal. That is, how often are you charged the interest, the fee for using other people's money when you're the borrower? Or if you're the lender, how often do you charge your borrower the interest rate? This is a dimensionless, just a number, but it's calculated by the time elapsed between P and F and the compounding period. So the units here are going to be time over time, and perhaps I will be able to explain. The most accessible way, the most common way to think about this is investing in a bank account. You might put in $100 and you might collect an interest rate of 0.05, that is 5% per year. N now could be expressed, because the compounding period is a year, as the number of years. 1 year later, you know you're going to have $105. And for most people, this is a straightforward equation. You've spent $5 to use 100 over the length of the year. You want 2 years? Change N to 2 compounding periods. Now we have 100 times 1.05 squared. And you know that's going to be a little bit more than 110, because you pay interest in the second year on the balance that accrued in the first year. That is, after 1 year, we already know it's 105. After another year, it will be 105 plus 105 raised to the 1. That's the interest in the second year, is both on the 100 and 5% of the $5 that was added to the balance. This is what we mean by compounding. And it gets pretty interesting when the interest rate is compounded more often than yearly. 5% per year, compounded monthly, requires an adjustment in our calculations. The monthly interest rate, that is the unit of time inside this bracket, must match the unit of time we used to compute the number of compounding periods. So in this case, if the difference between P and F, that is the future date that we're computing for, is a year ahead, that's 12 months. I've divided 5% per year by 12 to convert it to 5% per month. And there are 12 compounding periods. So the future value of $100 today, invested at 5% per year, compounded 12 times, that is compounded monthly, is going to exceed 1.05. It's going to be more than 5% per year. The difference between the difference between what's called the nominal rate, the 5% per year, and the effective rate is compounding. So the effective rate is computed in here. It's compounded monthly, and so it goes up. It's more than 5% per year, because every month you pay a little bit of the interest on top of the interest that was added in the previous month. So here, I started with P equals F over 1 plus I to the end, and I rearranged the equation 1 plus I to the n multiplied by P also equals F. What we're doing is looking forward in time. When we're going forward in time, we start with a P and we're working towards an F. That's called an interest rate. When we're working backwards in time, when we have a question like, how much would we have to invest today so that we have $105 a year from now, we're working backwards in time from an F to get a P. And that's when we call it a discount rate. Let's take this example. We might say P equals that F 105 divided by 1.05% per year compounded monthly raised to the 12 compounding periods in a year, and then compute for P. How much would you have to invest to ensure that you have $105 at the end of the year at 5% discount rate compounded monthly? You can see how this applies now to civil engineering works. If I'm expecting a benefit in some future year, or even a series of benefits every year, collecting $1 million, maybe the benefit comes from avoided fatalities at an intersection. I upgrade the intersection, I add signalization, I add some barriers and physical features, and I've reduced the fatalities. I translate that savings in fatalities into financial figures, and I say, over the next 20 years, we're going to avoid $1 million a year of fatalities at this intersection by investing in this project. You say, well, I wonder how much, aside from the lives lost, I wonder how much would I be willing to pay today to reach a financial benefit from the project? And you would do it like this. 1 million after the first year divided by 1.0, we're going to keep this 5% discount rate and we're going to compound it yearly to the 1. And that is year 1. Year 2, 1 million divided by 1.05 to the 2. Year 3, 1 million at the end of year 3 divided by 1.05 cubed, etc., until we get to year 20. $1 million in avoided fatality savings divided by 1.05 to the 20. You add all of these up to get P. The discounted savings in the first year, in the second year, in the third year, etc., all through 20 years, the expected lifetime of the intersection, sum all of those discounted values up, and we would get the present value of all of these savings. And that's an estimate. It's a lot less than $20 million, but it's an estimate of what we would be willing to invest in the intersection upgrade if we were only looking at it from the standpoint of financial perspective. This equation, which Excel is very good at doing, it gets repetitive. And so when you have a series of benefits such that the cash flow diagram looks something like this, the same amount of money to the good. In this case, expenses saved $1 million a year for 20 years. And we want to know how much should we invest today in order to realize these savings at a discount rate of 5% per year compounded annually or yearly. There's a special formula that will condense this repetitive calculation. I'm going to write it on the board for you now because it will apply to several of the problems that we see in the future. It is P equals, this time we're calling it A, not F. F would refer to one single payment at some future date. But A refers to an annuity, an annual constant series of payments. In the numerator, 1 plus I, the discount rate, raised to the n, minus 1. and in the denominator, I, the discount rate, 1 plus I raised to the n. You can use this for annual compounding, monthly compounding, as long as you're careful to adjust the discount rate by the number of compounding periods per year, when your discount rate is expressed annually, and then compute the number of compounding periods correctly. If it's monthly, then you're going to multiply the number of years, in this case 20, by 12. This would be 240. This formula condenses that cash flow diagram that we saw earlier into one calculation that will express the equivalent value in present value terms of this future annuity. So we're going to take these two equivalencies from F to P and from A to P, and we're going to look at some example problems and how to interpret a word problem, create a mathematical problem, and then solve it.